Okay, so now we're going to move on to confidence intervals, and this is results from our sampling distribution. Because of sampling distribution, the central limit theorem, the normal approximation to the binomial distribution, this lets us know we can use this calculation because we know we get normal distributions as long as this is correct, right? As long as we get that normal distribution, that normal shape when we graph it. We could go graph it. We don't have to as long as we know this is true. So what we're trying to do is we're trying to estimate the population proportion. We don't know what it is. I mean, before in like that example about the pets, the people locking their pets over the answering machine, they gave us an estimate of that. Remember that 34% of people talk to their pets. Well, now we don't know it, and we want to be able to come up with it. So population proportion, we're trying to estimate. My Oxbow kids, students, they're statistics students. One time, my partner professor from White Mountains, they come in, they get dual enrollment credit if they take my Oxbow course, and they match me up with a professor over at White Mountain Community College, and he comes in, makes a visit once a year, it's just to give him the course evaluation, really. But he asked him, they said, what are you working on? They said, confidence intervals. And he said, well, what does a confidence interval do for you? They couldn't answer it. I was a little embarrassed. So I'm going to make sure you guys know, at least hear it. So population proportion. What a confidence interval does, it estimates our population proportion P. We don't know that parameter. We're going to use our sample to make a good estimate of it. So what we're going to do here is you got a p hat from your sample, and here's the formula. I'm not going to ask you so much to use the formula. It's something you're going to see in the MyOpen Math, and I'm going to ask you this on the exam at the end of the course. This part here is your margin of error. That's the plus or minus. I encourage you to go out and take a look at the polls for the presidential campaign coming up here. At least I'm recording this in fall 2019. You know, you're going to see a lot of confidence intervals for the polls about who's ahead, who's winning, who's got the majority. It's all based on this stuff. This is the margin of error, and here's our sample. This is our point estimate. I haven't really talked too much about this, but in case I asked you, my point estimate is my result from my sample. And that's our best guess of what the true proportion is, of what P is. And then to get a better guess, then we're going to create a confidence interval. And this takes into account all the wiggle room from all the possible samples. Because we know the distribution, right? We know the distribution of all these little P hats. See, I don't know what P is. I don't know the population proportion, but I can go out and calculate a P hat. And you saw this with that guy's video about the pile of P hats. Even though we don't know the population proportion, we know how these sampling distributions behave. And we know that P hat will pile up around the true proportion. There'll be very few of the samples will have a result out this far. So it makes a really good estimate. That's why we come up with, here's a P hat, and then we come up with a margin of error, and that way, inside the margin of error, that'll capture our true P, even if we don't know it. Okay, so point estimate might miss it, but our margins of errors should catch it. Okay, so if you have a graphing calculator, it's if you do stat, arrow over to test, and you gotta scroll down. I have a graph right here, just a minute. I have this written in my classroom here at Oxbow. Not many of you probably have a graphing calculator, so that's why I don't emphasize it. But in case you do, this is a one prop Z interval on my calculator. It's choice A. So if you do arrow to stat, test, come down to A, and it says one prop Z interval. So you can use your calculator if you have it to do this. I'm going to show you how to use this Rossman chance applique. That works very slick, and it's free, and it's online and easy to grab a picture of. Okay, so let's calculate a confidence interval. We'll do a little bit of the formula setup just so you see it, and then I'll show you how to use the applet. Okay, so this is back in '77. Came from an old stat textbook. Three bills make it illegal for an employer to force an employee to retire at age 65, which is true now. They can't force you to retire at age 65, but they kind of get rid of you. It depends. They can get rid of you, right? So they did this survey, and they don't tell us it's a random sample, but we're going to assume it's a random sample because that's one of the requirements for this. We can't use this if we don't have a random sample of some sort. Simple random sample is best, but they don't always use a simple random sample. But as long as we get a random sample, if it's a convenient sample, it's garbage, you know. You really can't use it for anything. So how many people were in the sample? Well, let's see. I'm seeing 300. How many people wanted to keep working out of that sample? I found that they found that 21. See how they snuck that in there in text? So 21. So what's our sample percentage? Well, that's 21 over 300. And if we make that a percentage, or we can make it a proportion. So 21 divided by 300 is 0.07. Or 7%. So about 7% of people, based on the sample, still wanted to work. They were forced to retire back in 1977. So that's our point estimate, right? We know that's our p-hat. That's our point estimate of the percentage of people that were forced to retire back then. So now we want to get a better estimate. So we'll come up with a standard deviation for the sampling distribution. Now, before this, the other video, when we're dealing with the pet owners, we were able to use that 34% because that was a population proportion. We don't have that population proportion, so we're going to use our best estimate of 7%, and then 1 minus 0.07, and then over our sample size. Why didn't I write this out as a formula? I did say I was going to write a formula. For some reason, I didn't write that. So this is p-hat times 1 minus p-hat, or you can do p-hat as a percentage and do 100 minus p-hat if you want. Be careful with that because my open math might kick that back at you. Over the sample size. So we're going to go 0.07 times 1 minus 0.07 is 0.93 over our sample size of 300. And we'll crunch that. We'll do 0.07 and 0.93. So let's see, 0.07 and 0.93 divided by 300. I'm getting, well, again, I probably ought to read this to you because I know some people will not understand what a calculator is giving them, whether it's a phone calculator or online. My calculator is telling me 2.17 e negative 4. Well, that means 2.17 times 10 to the negative 4, or 0.000217. Now, I haven't taken the square root of this, just so you know, if you're a little confused. So I'm going to take the square root of that answer now. And that's going to be my standard deviation. So 0.147 I'm going to go with. So that's my, so I've got, I know this is normal. I'm not going to talk about it as a standard, as a sampling distribution. We just know that this is the standard deviation of all the possible p-hats based on our sample. Now, how many standard deviations do we need to capture the middle 95% of samples? Well, if we think about the 68, 95 rule, that's 2 standard deviations. We're going to get a little bit closer, make it a little more exact, because this is what the software does. A minute, I'm going to pause this video for a minute and open up a spreadsheet for us, or open up a table for us. So this is the z-score table. I haven't shown you this too much, many of these, but these z-score tables always record areas to the left. Now, if I have a 95% confidence interval, that's what I typically want. I don't always want a 95%. You'll see that I'm going to ask you to find something else, and we'll talk about how to get that. If 95% of my distribution in the middle, 5% is outside of it, So 0.025 is below it, 0.025 or 2.5% is above it. So we're going to look in our table in here as close as we can get to 0.025, okay? We'll put 4 decimal places. Okay, so let's see if I can't scroll it down at the screen right here. Okay, good, I can. So 0.025, look at that right there. So that's negative 1.96. See how the 6 is up there? I'm not going to make you read this, guys, these tables, but I want you to show where it comes from. Here, I guess I'm a little off. It's 1.96 was the 2.5%. So that's the z-score that cuts off the middle. It's a little more exact than plus or minus 2. We're going to use plus or minus 1.96. And if you scroll down here at the bottom, let me erase this. You stop the video, screen capture this. You want that little table, little mini table. This is just a subset of this table up here that gave it to us. So when you have a 95% confidence interval, you want to use Z. This is Z equals 1.96. Okay, and that's how many standard deviations we need to travel away from to get to capture the middle 95%. And there's technological ways to do this. We can show you those later if you need them. Okay, here, let me see. Can I scroll this down? I can. Okay, so the margin of error, I guess I should have given you, well, you know what the margin of error is. It was on that other sheet of notes, the handwritten one I showed you. So the margin of error is going to, well, it's the, let's do the margin of error. Yeah. So the margin of error is going to be the Z star, that critical value of Z that cuts off how many standard deviations away from the mean we need, times the square root of p hat times 1 minus p hat over n. So we've got 1.96. And didn't we already find the standard deviation for this? Because it's going to be 0.07 times 0.93 over 300. I think we already found that, didn't we? Let's see. That's right there, 0.0147. 0.0147. So 1.96 times 0.0147 is going to be our margin of error. That's going to be the wiggle room. So times 1.96. So that's 0.029 I'm going to round to. And our sample proportion was 0.07. Actually, you know what we're going to do? We're going to round a little even heavier than that. We're going to make that 0.03 just to make our math easier. So my lower bound, I'm going to take 0.07 and subtract 0.03 from it. That's what the plus or the minus means. So that's 0.04. And then I'm going to go to the upper bound. I'm going to do 0.07 plus 0.03. So that's 0.1. Okay. So that's my lower bound. That's my upper bound. So what does this mean? This means maybe we'll go check with an applet in a minute here, folks. I think I want to do the next little piece here with this confidence statement. Then we'll come back to it. So what we just found with that confidence interval, often they'll write it as looks like an ordered pair. If you've done pre-calculus or algebra 2 or college algebra, you've learned about intervals, and that's what this is. It goes from negative, so from 0.04 up to 0.1. That's what our confidence interval was. This is the lower bound. That's the upper bound. We are 95% confident. Here, I got the percentage there already, so I guess I don't have to write that. That the true percentage of people who were forced to retire is between 4% and 10%. and we did some pretty liberal rounding there, but that is probably, this is probably the most important thing you can do, because what you're going to do is you're going to get to use technology for this. I want you to understand what the technology is giving you. Okay, so let's go back and use that applet now. Actually, I'm going to have to link differently. It's this Rossmann Chance applet. It works really slick. Let me come back to the course modules, online tools. In the document that you have, it opens up. I've got the actual links if you want to look at the PDF. Here we go. 1 and 2 sample confidence intervals. It's going to open. There we go. What you're going to do is you're going to select, see, there's all these different options. 1 proportion, 1 mean, 2 proportions, 2 means. We're going to go with 1 proportion. We had 300 in our sample. So you don't have to do all that work we just did if you use this applet. And then our count, there was what? How many were there? There were, I wrote that down somewhere. 21, wasn't it? Going to calculate it. Then what we want to do, and that's right, 0.07, 0.0, we want to select confidence interval. It asks you what's your level of confidence. You calculate it, and notice we rounded pretty liberally. They're saying 0.0411. We rounded to 0.04 and 0.0989. So that's about 10%, right? If you do some rounding. So right on what we had. What I would do if I were you and I had to complete this work, I would use this applet, and then I would write that down as 4.1% to 10%. That would round enough. Now, my open math is going to want those a little bit more exact. They probably aren't going to want the percentage unless they say that. Okay, so that's how this Rossmann Chance applet works. Works really, really well. Okay, so I don't think I did another example of this, but there's plenty in that OpenStax textbook we can look at if you need help with. And also out of my open math exercises have you do quite a few of these. Okay, so the other kind of confidence interval we need to worry about is with sample means. Before we're doing that normal approximation, categorical variables. Now we have a quantitative variable that we're going to measure. We want to come up with an average. So here what we're trying to average, we want to estimate, I'm thinking back to that professor that asked my students what a confidence interval did, and they couldn't tell me. We're trying to estimate a population mean here, and that symbol is this mu, the Greek letter mu, and we're going to do this from X bars. Notice there's some requirements. Remember how we had to meet that normal distribution with a normal approximation? We had to make sure that we got a normal curve. Well, what happens with the central limit theorem, and you kind of saw this in some of that other videos, as long as your sample size is bigger than 30, well, let's see, I guess I did a couple of things here. If our sample size is bigger than 30, that's the sweet spot. If our distribution, our sampling distribution will be normal. So even though we don't know what mu is, all our X bars will fall around it in a normal distribution. It'll center, and most of them will be close to the true average, and we can use that to estimate it. Because then again, when we find the margin of error, it'll capture that margin of error, will capture the mean. If you have a sample size less than 30, well, we'll talk about that in a second. I did say if we know the population standard deviation, but we never know the population standard deviation, really. I mean, we never know that. So it's kind of a crazy thing that stat textbooks do that. I'm not going to have you do any exercises or do any test questions where that happens. But notice the formula for the confidence interval is very similar. There's my point estimate. There's the sample mean. That's our best guess. And then we come up with a margin of error again. See that critical value of z? That would be the same one that we used with the proportions. And then the standard deviation is a little different. I think you saw this in the video. You take your standard deviation by the square root of your sample size. Instead of that square root of p times 1 minus b, a little different. So that's what happens when you know the population standard deviation, right? And you get a sample size bigger than 30. If you have a sample size less than 30, but you know the population standard deviation, and you know the original population was normal, you're okay. This still all holds. So now what happens if, and I said that, if we know the population, is normally distributed, and we know the population standard deviation, being less than 30 is still okay. What happens? Let's come down here. Let's come down to the next one. Okay, so then what happens if we only know the sample standard deviation? Well, if we don't know anything about the parent population, as long as we have a big enough sample size, we're good to go. We can use these techniques to find it. If we have a sample size less than 30, small samples, but we know the population is normally, that we drew the sample from, and normally distributed, we can still use these techniques. The problem comes in if we have a small sample and we don't know anything about the parent population. You can use these techniques, but your answers are, you don't know what's happening. They have other non-parametric tests that you can run. We aren't going to look at those in this course. That's a Stat 2 course, a Stat 2 topic. Okay. Everything I'm going to do for you, I might ask you to tell me if this is valid or not. But look at a result, look at a sample, and I might ask you, is it safe to use these techniques? And then I'll probably say, with that in mind, we're just going to run it anyways. Notice before we were using Z, and now I'm talking about the T interval. Well, the T distribution, look it up. You're going to want to look about the students' T distribution. And it's not because students are newer students. It was a pseudonym for this guy. Go see it. It's connected with Guinness Brewery. It's an interesting little story. You can find it on Wikipedia. I won't take the time now to go into it. It's a good story. So we do need to use a little bit different tool for it. That table, that normal curve table, won't work here because this is the Z table, not a T distribution. Now, interesting enough, there are T distribution tables. Okay, and the one thing you do with it, one thing you do need to know, if you look at this, you remember that 1.96? Look at the 95% level of confidence. This is going to be, notice how the degrees of freedom out. With the degrees of freedom is your sample size minus 1. Notice how the critical value of T, this is the number plus or minus the standard error or the mean there that we've got to calculate. Notice how as the sample size gets bigger, the degrees of freedom gets bigger, these numbers get smaller until you come down to, let's see, if we come down to, you start getting down towards a sample size of 400, say, notice how that's getting really close to the Z-score of 1.96. So it gets there eventually. We don't really have to worry about this. Oh yeah, look at that infinity. Infinitely big, you go to the Z-score value. We're going to let software drive this for us. I'm not going to make you look up a T distribution. If you do in math, there's ways to do it. I don't think I asked you that. I'll have to go take a look. If there is, I'm sure there's a video I made to show you how to do it. It's a little piece though, not the big picture. So don't get shook about that. Let's come back and do this problem now. So I have got confluence, as I said that, and I told you we don't know the population standard deviation. So this is that same question about the old drug, the old pain relief drug, bringing relief in 3.5 minutes. That's an aside. We don't need this to calculate the standard or calculate the confidence interval. So, but we do know that the sample mean X bar here. Let me make this thinner and go to black ink. X bar is 3.2. The sample standard deviation was the 1.14. The sample size was 50. So we've done these calculations already. So we know that let's see, did I ask you this down below? Yeah, we'll skip the sketch for a minute. We already did this before. I think I just copied and pasted it. 1.14 over 50, and I don't remember what that was. You probably have access to that right here on your notes. So 1.14 divided by the square root of 50, I'm getting 0.161. I know I made this sketch on the other page, on the other note. So I'm not going to do that again right now, just to make this a little quicker, because that Grossman chance applet will give this to us. Oh well, it won't. Will it? That would be the David Lane. But you have it down in your notes, so I won't bother doing it here because it's the same. So what's our let's see. I guess we got to do the formula. Did I not give that to you, or did it wrap down to the second page? There we go. So that's the formula to calculate a standard or confidence interval. Again, that's the margin of error, the plus or minus part. Here's the X bar. So we know 3.2. Now, why didn't I give you? Let's figure out what we need for a T star, just so you see it. Again, I'm not going to make you do that. We know n equals 50. So that tells me for the degrees of freedom, it's n minus 1. So 50 minus 1 is 49. So we want a 90% confidence interval. So I'm going to come back to that T table. I'm going to erase this so it doesn't get in the way. Back in the old days, we had to do this. What do we had? 50. So my degrees of freedom is 49. And I want a 90% confidence interval. 49. So right there is my critical value of T, 1.677. So you see how I did that? The degrees of freedom is right there. I said my level of confidence. So that's the T star, that critical value of T. So we're going to go 1.677, was it? Short-term memory problems here. 1.677. All right. And there is an inverse T calculator. Why do I have this linkable here? I know I have it linkable in the document. Let's see here. Let's go find that. Notes week 4. Let's go find that. I want to do that just so you see how to do that. That's the Grossman chance. That's a confidence statement. There, we're coming there. Kind of like being in the classroom and having the professor stutter, huh? So let's see here. Here we go. Let's click on that. Yes, I want to allow it. I want to go there. I want to erase this. So here's how this applet works. Notice it wants, so if we want a 90% confidence interval, that's 10% outside of it. That lower area is 0.05. That upper area is 0.05. That adds up to 10%, right? You're going to see this. If you look at some other textbooks, you're going to see T alpha divided by 2. The alpha is the stuff outside. So 90%, the outside is 10%. We're going to divide it by 2, make it a decimal. If you have a 95% confidence interval, the alpha will be 95 in the middle. Outside is 5%, so it's going to be 0.05 divided by 2. If we have a 98% confidence interval, that's 2% outside of it. That would be 0.01. It would be 0.02 divided by 2, right? You could get that right here. It would tell you the T-score you would need. It works pretty slick. But we're doing a 90%, so we've got an outside area of 0.1. So numbers. 0.05, right? 10% outside, so 0.05. Okay, we've got 49 degrees of freedom, and that's the z-score we need. Just a little bit more than 2.0096. Notice this is a little more exact than what did the table tell us? What did I write here? 1.677. Oh, that's weird. What did I do? Did I do something wrong? "49 degrees of freedom." "49 degrees of freedom, 9% comfortable, 1.677. Let's go back to this now. Oh, I bet you what I did. Here, let's try this. Let's put 0.1 here. There we go. So this is because I had to, for the table, I had to go to a one-sided. Here it'll do it for me. So do you see how that works? So all I had to do was come up with the outside area, and it'll cut it in half. Small part of a small idea, guys. At least now I've got the same t-score. Okay. Calculators will do this too. Alrighty, so our margin of error is going to be 1.677 times our remember it was S, it was 1.14 over the square root of 50. And we already had done that. We had said it was 1.677 times, let's see, do I have it right here? 0.1612. I'm going to multiply that on my calculator times 1.677. So I got 0.27 that I'm going to round to there. So then to get our confidence interval, where I really broke this up, it was 3.2 was our mean for the new drug. We're getting a margin of error of why don't we round this to 0.3, right? 0.27 rounds to 0.3. So our lower bound will be 2.9, because remember it's 3.2 minus 0.3. And our upper bound will be 3.5, which is 3.2 plus 0.3. And then we will check with the applet, but I think I want to write the confidence statement first. So I'm 90% confident the true mean time to relief, i.e. for the new drug, is between 2.9 minutes and 3.5 minutes. Remember how they said the old drug had a mean time to relief to 3.5? Remember how when we did this with the sampling distribution and we said it wasn't really significantly faster? You see how this confidence interval catches that 3.5? That's another flag that this new drug might not be working as advertised. It's faster. That gives you a faster mean time of relief. So that's the so what. That's kind of more like next week where we're going to go with this. Let's go use that Rossman chance applet again. Let's see. Theory-based, this one here. Instead of one proportion, we're going to do one mean. Now, this is a t distribution calculator. It doesn't use z distributions. You can find those offline, online somewhere, but like I said, we're not going to really worry too much about it. Now, I believe this was, let's see, where's my numbers here for this? It was, let's see, there was 50 individuals. The mean time to relief is 3.2. And our sample standard deviation, we're not going to do that calculated one. We can just give the one that came from the sample. This calculator will do it for us. So I'm going to type in that's the standard deviation for the sample, not for the sampling distribution. We'll let it calculate it. We'll do a 90% confidence interval, because that's what we changed it to. And we'll calculate it, and look, that is about what we calculated doing all that work. Okay, So you just got to make sure you set up your sample size, get your mean. This is your sample standard deviation, not the standard deviation for the sampling distribution, or we also wrote that if we were the population standard deviation. Change your level of confidence, make sure you have confidence levels checked, and then that's your result. And then you can just translate that into your statement. Okay? So I think that's all my examples. I hope this helps you do the calculations. I encourage you to at least do the MyOpen Math. You got to do the MyOpen Math for homework, for problems. And there's all videos. Those are my videos. Most of them are my videos that I adapted for it, put into for it. We can also do some exercises out of that OpenStax textbook. There's a lot there. Let me know what you need for help with this.